In this session, I want to emphasize a concept that we already introduced in the last few sessions. The concept is called wavefront. And a wavefront is very important to describe a wave. I said already that when we observe a wave in motion, in fact, we are looking into a particular point at the wavefront. And we also name waves according to the shape of the wavefront. For example, if I have a spherical wavefront, then we call this the spherical wave. And if I have a cylindrical wavefront, I call this cylindrical wave. And if I have a planar wavefront, then we call this a plane wave. And in general, the description of the motion of the amplitude of those waves is given by this wave function. And this argument is quite important, t plus minus r over u, because if you set this the t plus minus r over u to be a constant, then you'll be looking at a particular position of the wavefront. So this is if you set this to be a constant, say phi 0, then r is going to describe a wavefront of the wave for you. So let's first look into this sinusoidal wave because now we pretty much will emphasize on sinusoidal wave because it's quite simple and compact in the form and also very useful when we do analysis. So in this harmonic wave described by this, we say amplitude and then cosine omega t minus kz plus theta 0. The wavefront is a surface with a constant phase. So they set this phase into a constant value, and then suppose that we freeze time at t0, and it tells you that the wavefront is described by this z equal to a constant. This means that you have planes with the surface normal along z direction like this. The z direction is just perpendicular to those surfaces. So it's a plane wave with a wavefront along z direction. So this k multiplied with z, in fact, can be considered as the two vectors dot product together. K is along z direction, which is the wavefront normal direction, and z is just a position vector. So let's write k equal to an amplitude multiplied with the unit vector along z direction, which give you the wavefront propagation direction, and it's perpendicular to the wavefront direction. Now, suppose we have a k vector along some arbitrary direction like this with three components in the x, y, z coordinate system. You have x component, y component, and z component. And there's a certain amplitude associated with it. And we already know that the k wave number is equal to 2 pi over the wavelength. And this an is going to tell you the direction of the wavefront. So think about that you have a few planes which are the wavefront of the sinusoidal wave. And perpendicular to this wavefront is the unit vector denoted by an. So now, in general, I can write the sinusoidal wave, the harmonic wave, into this form by replacing previously k multiplied with z with this k dot r, these two vectors. And the r is just, in general, position vector, x ax, y ay, and z az. And so this is a position vector. So now let's set this to be a constant, because we argue that if you set this phase to be a constant, then we can construct the plane of the wavefront. So that's the fixed time, take time, say equal to 0, and then you have k dot r equal to a constant. And you can figure out that this k dot r equal to a constant basically describe a plane in space because if k along this direction, that with the position vector give you a constant length, which is the length from here to here, perpendicular to this plane, then this k dot r equal to a constant describe this plane. So now it's quite clear that for this kind of solution, cosine omega t minus k dot r plus y0 is going to describe a plane, a planar plane in xyz coordinate system. But if you change this coordinate system to a spherical coordinate system, then this can explain a spherical wave. But for now, we describe this wave in the xyz coordinate system. So we express this position vector as the xyz variables. So k dot r give you a plane in this xyz coordinate system. Now, want to see the importance of the wavefront. I want to emphasize that a wave always has a wavefront. Without a wavefront, a wave cannot be called a wave. So imagine that you have a wave instant on this boundary, which is the boundary between two materials, materials 1, material 2. And because these two materials will allow the wave to propagate at different speed, so the wavelengths inside these two materials will be in general different. In optics, we like to describe the wavelengths to be equal to the vacuum wavelengths divided by the refractive index of the material. But the wave propagating in material 1 is a wave. When this wave propagates into the second material, it is still a wave. So we need to have wavefront well defined on the boundary. So if we look at this diagram at the boundary, the wavefront are connected to each other. So this is a condition that a wavefront has to be continuous at the material boundary. And this is because that the wave is well defined by the wavefront. Given this condition, and then we draw the k vector, the wavefront vector for the first wave, and also draw the k vector for the second wave. And you can see a so-called instant angle, which is the k vector, the angle between the k vector and the surface normal direction. And you have transmission angle, theta t right here. Given these two angles, if I calculate the length of this L, then I can relate the wavelengths in these two materials through the instant angle and the transmission angle. With this results, and then I put this wavelength scaling in different materials into this expression, then I can organize it into the famous law called Snell's law, which tells you that n1 sine theta I is the instant angle, is equal to n2 sine theta t. Theta t is the transmission angle. So Snell's law is a consequence of the wavefront continuation on the boundary. And this result can also be constructed by making the k vector continuous on this boundary, because k vector describes the wavefront. So based on this wavefront continuation concept, we derive the Snell's law, and this Snell's law is very general and very universal. It applies to all kinds of waves, and not just to the electromagnetic wave, because up to this point, we haven't taken into account any electric field or magnetic field in this problem. We just require the wavefront to be continuous at the boundary, and then we have these results. So in this section, we point out a few important things. Number one, 第一件事情我们提到就是一个波的话，有个波前在那个地方，波前的这个传播方向呢，就是跟这个在我们讨论的问题里头呢，是跟这个波前的方向呢是互相垂直的。那这个方向呢是由这个 k vector 来表示。那在一个这个 harmonic wave 里头呢 k dot r 等于 constant 呢定义出一个波前的这个形状给你。那我们在这个物质的边界上头要求波前连续的话呢，就很自然的得到所谓的 Snell's law。所以 Snell's law 呢是相当这个广泛这个可行的一个公式，因为所有的波在一个介质的界面上头呢，都会这个 follow 这个 Snell's law， 因为在推导的过程里头，我们只是要求这个 wavefront 是一个这个连续的一个状况。那这是几个重点供你参考，谢谢。